Hi folks, Chris McClure. We're just skipping right over section 7.1 and going right into talking about estimating population proportions as our discussion in chapter 7 and estimating various estimates of measures of center for population. So we're going to be talking about proportion here in section 7.2. 7.3 next time we'll be talking about estimating the mean, and then after that we'll be talking about estimating a measure of variation in the form of standard deviation or variance in section 7.4. For today we're talking about population proportion, so estimating thereof. So kind of a longer discussion today, and that's why we're covering or skipping over section 7.1. The basic idea here in all of these sections in chapter 7 is we're coming up with a point estimate. And a point estimate is just a fancy way of saying that we are coming up with a single number to estimate some sort of quantity. In this case, it's the population proportion. Now, as I've said many times, we typically don't know the size of the proportion, let alone much else about the population. I mean, and but we can estimate the proportion, as in, for example, the fraction of people in the community who support Smith for mayor, or the proportion of residents of Iowa who support gambling, that sort of thing. There's no practical way for us to know everybody's view. But, if we just take a good representative sample, a sample that's representative of the population, and ask them the question, do you support, Grandstad for re-election, yes or no? And then take the number of people in our sample who said yes, divide it by the total sample size. That'll give us a sample proportion, which is a point estimate for the actual population proportion. We don't have the resources to ask everybody in the population, but we can do a pretty good job in estimating it, but with this point estimate. We can also construct a confidence interval, and by the end of this discussion we'll see how to construct a confidence interval to estimate the true value of the proportion. And we should know how to interpret such confidence intervals. And lastly, we'll talk about how to find the appropriate sample size necessary to estimate a population proportion. All right, moving along here. So what exactly is a point estimate? It's a single value or point, aka a number, that is used to approximate a population parameter. Parameter, as in population mean, population parameter, or proportion, population variance, population standard deviation, which we probably will not know, but it's going to be estimated by the sample mean, by the sample proportion, etc. We are talking about the sample proportion. P hat, which is a P with the little hat over the top, is going to be what we use as our estimate of the population proportion. We say it's the best point estimate because it's the one and only unbiased estimator of the actual population proportion. We talked about what it means for an estimator to be biased versus unbiased last time. Actually, several lectures ago. Let's take a look at this example. The Pew Research Center conducted a survey of 1,007 adults and found that 85% of them know what Twitter is. Now, what is 85% of 1,007? So if you were to do that calculation, 85%, which means 0.85 times the quantity population, in this case 1007. That's approximately 855.95. That's 855. So that's approximately 856. And of course, you can't have a fractional number of people, so we'll round that up. So that tells us that 856 people out of the 1007 people who were polled, 856 said that they knew what Twitter was. And of course, 856 divided by 1007 is 85%. So the proportion of people in your sample who said they knew what Twitter was 85%. But we typically write it just as a decimal. So p hat is just 0.85. Write your sample proportions as decimals. Okay? Now we're going to talk about computing a confidence interval, otherwise known as an interval estimate. And it's a range or an interval of values used to estimate the true value of the population parameter. So here's what it looks like on the real number line. On the real number line, we got the set of real numbers, and we're going to calculate p hat. And then we're going to come up with a margin of error, which is, some number. And we're going to add it to p hat. We'll also subtract that margin error from p hat, so that we have this interval of numbers. And we're going to say that this is a confidence interval, in which we say that there's a certain amount of confidence, aka probability, that this interval actually contains the true value of the parameter p, which is the proportion, the population proportion. Now, we don't expect, and we shouldn't expect, that p hat is going to be exactly equal to p, but we will expect with a certain amount of confidence so that our interval here will contain p. Now, p doesn't change no matter what sample that we get. The interval, because of the fact that you have p hat here, p hat and thus the interval will change from one sample to the next. But p doesn't going to change. So if you have a 95% confidence interval, then if you were to do this experiment, say 100 times, 95% or 95 out of those 100 intervals will actually contain p. Confidence level is the probability of 1 minus alpha. By the way, I'll tell you what alpha is. But alpha is just going to be some number between 0 and 1. Typically, it's going to be small. Something like 5%, 10%, 2%, 1%. So that means 1 minus alpha will be rather large. 95%, for example, is the typical confidence level. It's the probability expressed as the equivalent percentage value that the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. So instead of taking one sample, we can repeat this process many, many times, in which each time that we do a sample, we calculate p hat and come up with the interval. And 1 minus alpha will be the proportion of times that the interval should contain the parameter p. The confidence level is also called the degree of confidence or the confidence coefficient. Typically, your confidence level is 90%, 95%, or 99%. Of these three, 95% is the most common confidence level. And I would dare say about 95% of the problems asking you to do a confidence interval is going to be with a confidence level of 95%. Now, when we have a confidence level of 95%, think about 95% is 0.95. 1 minus that is 0.05. So that would correspond to an alpha level of 0.05. Just like 90% confidence level corresponds with an alpha level of 0.10. Or 99% confidence level corresponds to an alpha level of 0.01. Okay? We have more to say about alpha in the coming times, but the confidence level and alpha, they go hand in hand. You increase one and decrease the other. Now, let's talk a little bit more about interpreting a confidence interval. Well, I'm just going to kind of read through these. We must be careful to interpret confidence intervals correctly. There is a correct interpretation and many different and creative incorrect interpretations of the confidence interval. So, for example, suppose that our confidence interval is such that P is between 0.828 and 0.872. Okay, so when we write that, we could say that we are 95% confident that the interval from 0.828 to 0.872 actually contains the true value of the population proportion P. This means that if we were to select many different samples of size 1007 and construct the corresponding confidence interval, 95% of the time, if we are using a 95% confidence interval, 95% of those samples would, when they result in a confidence interval, 95% of those confidence intervals would actually contain the true value of the population proportion P. And note that in this correct interpretation, the level of 95% refers to the success rate of the process of being used to bracket that proportion. Okay? Here's a quick caution here. Know the correct interpretation of a confidence interval. And that confidence intervals can be used informally to compare different data sets, and the key word here is informally. So we could talk about an informal basis, but we cannot make formal judgments regarding the comparison of multiple data sets. But the overlapping of confidence intervals should not be used for making formal and final conclusions about the equality of proportions. There's other tests that we can do about with in talking about the equality of proportions. We shouldn't be using the idea that, hey, you've got this one sample from this one population, you've got this other sample from this other population, and we, construct confidence intervals, and it turns out that the two confidence intervals overlap, or maybe they don't. We can't really formally make a statement regarding that the two population proportions are the same or not. Okay. If it turns out there is some overlapping or not. And we could use confidence intervals for hypothesis testing. And we will have a formal discussion of hypothesis testing next chapter, chapter 8. But I can tell you right now that a confidence interval can be used to test some claim made about a population proportion P. As in, you know what, I'm willing to bet that 1/2 of the population supports Branstad for re-election. For example. For now, we do not yet use a formal method of hypothesis testing, so we simply generate a confidence interval and make an informal judgment based on this result, as we shall see in this example here. Coming up, critical value is what alpha is. Standard z-score can be used to distinguish between sample statistics that are likely to occur and those that are not likely to occur. So you tell me what alpha is, and then I can find a z-score which separates that region under the curve of the distribution such that areas to one side, observations to one side are considered to be unlikely, and then to the other side of that z-score, those observations are likely. Such a z-score is called a critical value. We'll talk a lot about critical values. Critical values are based on the following observations. Number one, under certain conditions, the sampling distribution of sample proportions can be approximated by a normal distribution. We actually saw this when we talked about sampling distributions back in the previous chapter. And number two, a z-score associated with a sample proportion has a probability of alpha over 2 of falling in the right tail. Because of the fact that we're using a normal distribution, we could take the area in the two tails, divide it in half. If we want alpha to be in the two tails together, we could take alpha divided by 2 to get the area in one tail. Here's an example. Here we've got some normal distribution. Actually, it's the standard normal because z is equal to 0. And if I tell you that I want alpha to be equal to 0.05, for example, and if it's a two-tailed test, that means I want alpha over 2 in each of the tails. And alpha might be 0.05. Half of that is 0.025. Because of the symmetry of the normal distribution, 0.025 will be in the left tail and 0.025 will be in the right tail. And it's just a matter of figuring out what is the z-score here, there, and there. Now, a little bit of notation. When we see the z sub alpha over 2, that means we have a critical value associated with alpha over 2 in the tail. Again, this critical value, z sub alpha over 2, the z sub alpha over 2 is actually called the critical value. Alpha is not the critical value. But the z-score that's associated with alpha or alpha over 2 is the critical value. Critical value is a value of a random variable which separates the likely versus the unlikely observations. Now, looking at this picture right here, if we were to find z sub alpha over 2, it's a value of z, which is the standard normal random variable. And if it's positive, that means that, 1 minus alpha over 2, 1 minus alpha over 2 lies to the left. 1 minus alpha, what I'm talking about here is area under the curve for the distribution. Lies to the left of z sub alpha over 2. And alpha over 2 lies to the right. But here's alpha over 2 here in the left tail. So whatever z sub alpha over here, z sub alpha over 2 is on the right, we'll have the negative of it over here. And here in the middle, you have the middle 95% or whatever confidence level. Definition: a critical value is the number on the borderline separating sample statistics that are likely to occur from those that are not likely to occur. We're going to talk more about sample statistics in the future. This is probably the first time that you're seeing this term, but we will be computing sample statistics. based upon our data. The number z sub alpha over 2 is a critical value. That is a z-score. There are other types of critical values, by the way. This just happens to be the one that applies for proportions and means and stuff. Z sub alpha over 2 is a critical value that is a z-score with the property that it separates an area of alpha over 2 in the right tail of the standard normal distribution. If you see z sub alpha, that means that we're doing a one-tailed test, by the way, which you don't need to know about for this section, but I'm just giving you a heads up. So, but this is for a one-tailed test where all of alpha is in one tail or the other. Okay. Moving along here. So finding z sub alpha for a 95% confidence level. Well, let's pull out our z table. I don't know if I still have it up. Well, I'm going to go and pull up my z table. Now, 95% confidence level is most common, so that means that we would have 2.5% in the left tail and the right tail. Now, if we want to find the z value corresponding to 0.025 area in the left tail, now see this 0.025 value right there? That's probability. This area to the left. The corresponding z-score is negative 1.96. So that means that the critical value for the right tail is going to be positive 1.96. So for a 95% confidence level, we'll use the critical value of 1.96. And likewise, we could look up the critical values for 90% level, which means that you have 10% in the two tails or 5% in each tail. Okay, alpha is equal to 0.10. Remember, alpha is equal to the area in the tail or tails, depending on if it's one tail or two tailed. For our confidence intervals, it's always going to be two tails. And so if alpha is equal to 0.5, half of that is if alpha is equal to 0.10, then half of 0.10 is 0.05. And going back to our z table, if you were to look up 0.05, it'd be right here, that's closest, and you backtrack to find the z-score, negative 1.645, which is halfway in between there and there. So 1.645 is the critical value that's associated with an alpha being equal to 0.10 for two tails, aka for a 90% confidence interval. And if you want a 99% confidence interval, that means alpha is equal to 0.01. Take half of that. Half of 0.01 is 0.005. And again, going back to our z table, .005 so it's going to be somewhere in here, 0.005 for that probability. And you have a z-score of negative 2.575 or so. So 2.575 is the critical value associated with a 99% confidence interval. But the one that you probably need to memorize the most is 1.96, because most of our confidence intervals are 95% confidence intervals. So remember 1.96, almost 2, but use 1.96. So we're going to use that 1.96 when we calculate our margin of error that we use to construct our confidence interval. When data from a simple random sample, remember that? Remember what a simple random sample is? When data from that sample are used to estimate a population proportion P, so in other words, we calculate P hat from our sample, the margin of error, denoted by the capital E, the margin of error is the maximum likely difference with the probability of 1 minus alpha, such as 0.95. So if in this case alpha would be equal to 0.05. Remember that alpha is usually very small. So 1 minus alpha is typically what we see as the confidence level. 0.95, 95%. So the margin of error denoted by E is the maximum likely difference between the observed proportion P hat and the true value of the population proportion P. Maximum likely difference. Of course, we have no way of knowing because the population is probably going to be so large we don't have the resources to know. But statistically, and thankfully, the hard work has been done for us, so we don't really have to know a lot of the esoteric details. But the method guarantees that, the maximum likely difference is between P hat and P is going to be given by E, with the probability given by whatever 1 minus alpha is, or your confidence level, 95%, for example. Okay? So when we're talking about proportions, this right here is what's going to calculate your margin of error, where you take that critical value, z sub alpha over 2, times the square root of p hat q hat over n. You'll know what p hat and q hat are from your data set. You'll calculate those. And of course, n is the sample size. So this is a real easy calculation to calculate your margin of error. Remember, capital P itself, not capital P, but lowercase p is the population proportion. Now, don't get that mixed up with the little p from the binomial probability distribution. In this case, when we're talking about proportions, p, as in this lowercase p, without any ornamentation, means the population proportion. P hats means the sample proportion. N is the sample size. E is the margin of error. Z sub alpha over 2 is the z-score separating an area of alpha over 2 in the right tail of the standard normal. So we're going to talk about some things that we need to check before constructing our confidence interval. We need to make sure that we have a sample that is a simple random sample, not a convenient sample, not any other form of a bad sample, but this is a sample that is random and representative of the population. We also need to verify that the conditions for the binomial distribution are satisfied, and those are that there is a fixed number of trials. The trials are independent. There are two categories, two possible outcomes when you do each individual trial for your binomial experiment. So, for example, when you interview someone, ask them a poll question, they either say yes or no, or up or down, left or right, blue or green, whatever. There's only two possible outcomes. And that the probabilities remain constant for each trial. Lastly, number 3 here, there are 5 successes and 5 failures at least. So, when we ask 1,007 people whether they know what Twitter is, we need to have at least 5 people who said yes, and we need at least 5 people who said no. Okay? And here's how we simply calculate our interval. We take p hat and we add e to get the right hand side of the interval. We take p hat minus e to get the left hand or lower level for the confidence interval. Remember how we calculated e? We took our critical value, z sub alpha over 2, oftentimes 1.96, by the way, or 1.645, or 2.545 or whatever, depending on, of course, what alpha is. And alpha, like I said, is 1 minus the confidence interval, or confidence level. And then times the square root of p hat q hat over n. We have an example coming up. So p hat plus or minus e is what gives us our interval. By the way, how much precision should you use in expressing your numbers? First of all, I'll tell you is to avoid doing a lot of individual steps when you do your calculation. Try to put everything in your calculator to the greatest extent possible to avoid round-off error. And when you express your final answer, express your answer to 3 significant digits. Okay? Pretty much we can say that's 3 decimal places. So here's our procedure for constructing our confidence interval. So verify those assumptions that we talked about earlier. Find your critical value. After you do enough problems, you'll know the more common ones for 90%, 95%, and 99%. And then go ahead and calculate your margin of error using this formula here. And then take p hat plus or minus e. Make sure that you round it to 3 sig figs when you write your lower and upper limits. So let's take a look at an example here. Suppose that, and by the way, this is wrong. This is 0.85 here. Now, if you were to read the first part of Chapter 7, you'll see that there was what they call a chapter problem, in which the Pew Research Center poll of 1,007 randomly selected adults showed that 85% of the respondents knew what Twitter was. All you need to do was take the number of people who said, yes, I know what Twitter is, and divide it by the sample size of 1,007, and you got 85%. Okay, so the sample size 1,007, p hat is 0.85, and we're going to go through the steps of finding our confidence interval. Now, we want a 95% confidence interval. So we're going to find the margin of error, find the interval. We're going to ask ourselves, can we safely conclude that more than 75% of adults know what Twitter is? And then we will try to interpret our results. All right, so first of all, before we proceed, are we actually allowed to use these steps to come up with our confidence interval? Well, we have a simple random sample, yes. Fixed number of trials, 1,007 of them, yes. Each time that we sample somebody, we ask them the question. We have, one of possible two responses. The trials are assumed to be independent, or each individual will provide a response that's independent of anybody else. Probability remains constant because of the fact that, because they're independent. Each individual that we ask is going to be independent of everybody else. That's why the probability remains constant. And 85%, and like we already done this calculation before, 85% of 1,007, that means 0.85 times 1,007. I'm going to pull out my calculator and redo this. Round this to 856. So, yes, we had at least 5 people who said yes. And because 856 is much less than 1,007, there were at least 5 people who said no. So this last little bullet here is checked. Okay? Because we had at least 5 successes and 5 failures. Where I guess we could define a success as someone who says that they knew what Twitter was, and a failure is someone who said that they didn't know what Twitter was. Now we're going to go ahead and calculate the margin of error. You might remember that 1.96 is the critical value for that we use for a 95% confidence interval. Times the square root of p hat was 0.85. 1 minus p hat is q hat. Q hat is 0.15. These two numbers right here should add up to 1. And then divided by the sample size of 1,007. So if you take 0.85 times 0.15, divide by 1,007, take the square root of that, and then multiply by 1.96. And then you will get this margin of error. Make sure that you carry lots of decimal places here. And then you're going to take p hat plus and minus that margin of error. There you're subtracting the margin of error from p hat, and over here on the right you're adding it. And then after you do that subtraction or addition, and then you round to 3 decimal places, there and there. So we have our confidence interval from 0.828 to 0.872. Now, it would be wrong for you to say that there's a 95% confidence that the true proportion of people who know what Twitter is lies between 82.8% and 87.2%. Okay, that would be the wrong thing to say. The more accurate thing to say is that there is a 95% probability that interval actually contains p. Remember, p is fixed. Our confidence interval actually is dependent on our sample, which is random. We're going to answer this question based on the confidence interval obtained in the previous part. Does it appear that more than 75% of adults know what Twitter is? And the answer is yes, because if you look at the lower limit, that was 0.828, which is much larger than 0.75. So it's very likely that more than 75% adults know what Twitter is, because the lower limit for this confidence interval was 82.8%. Okay. And if you want to summarize the results that we just came up with, We could say that 85% of U.S. adults know what Twitter is because p hat was 0.85. That percentage is based on a Pew Research Center poll of 1,007 randomly selected adults. We could also say, because this was a 95% confidence interval, we could say that in theory, in 95% of such polls, the percentage should differ by no more than 2.2 percentage points. Where did that come from? That was E, right? In either direction from the percentage that would be found by interviewing all adults in the U.S. Now, real quick, when we look at the results of a poll, they're telling us results, point estimates of the proportion of people who, support candidates or support a hike in the gas tax or support the performance of the president or whatever. Typically, it's binary. They approve or they disapprove. Sometimes it's more, because you have more choices. Anyway, we should, regardless of what the poll is, some things that we should consider. Number one, was there a simple random sample? We probably won't know that if we are the casual consumer. But if it's done by a professional polling organization, I'm sure it is. But if you're looking at someone who's not very trained in statistics, you might want to ask them how did they, do their sampling. We want to be careful to minimize the voluntary response sample where we're only dealing with people who chose to participate. You actually have to do as good of a job as you can to compel everybody that you chose for your sample to actually respond. Otherwise, if you only are going to be lackadaisical and just care about those people who chose to respond, you're going to get responses from people who have a strong opinion, and that means that your sample is going to be highly biased. Anyway, number two, the confidence level should be reported. Okay, sample size should be provided, which it actually typically is in the fine print. And the quality of the poll results depends primarily on the sampling method and the size of the sample. But the size of the population is usually not a factor. Again, population size is usually not a factor. If your sample size is really small, that could be a problem. If it's not so small but not very large, that is not a showstopper either. It's more important to have a quality sample. Okay, moving along here. Now, we're going to talk about what sample size should you have in order to get a given margin of error. Now, we're working backwards from what we did a few minutes ago, where we knew what our sample size was, and then we computed the margin of error. But suppose we know what the margin of error is. What is the sample size in order to produce that margin of error? Well, we're going to talk about how to calculate that. Now, remember that this is how we calculate margin of error, where we take the critical value times the square root of p hat q hat over n. Well, suppose that we know E, but we don't know what n is. Of course, we know what z sub alpha over 2 is. We know what p hat and q hat are. So if the only thing that we don't know is n, and we want to solve for n, we could divide both sides by the z sub alpha over 2. take the square of both sides, divide by p hat and q hat, and then flip everything upside down, then we would end up with this. Just a little bit of algebra to solve for n. Okay? So, you just need to plug in the critical value here for z sub alpha over 2 and square it, multiply it by p hat times q hat, divided by the margin of error squared. E needs to be a decimal, not a percent. Now, if you're going to do a survey or a poll, you're going to be wanting to find what p hat is in the first place. So what can you use for p hat when you're doing this calculation, when the whole purpose of your survey was to find p hat? Well, you could look at what previous work has been done, for example. Do a little bit of research, so you can at least get an estimate for p hat and thus q hat. Remember, p hat and q hat add up to 1, because q hat is 1 minus p hat. P hat is 1 minus q hat. But if we really don't have much a way of knowing what q hat and p hat are, then just assume that p hat are both equal to 1/2. So that p hat times q hat is 1/4, or 0.25. Okay? So I think we have an example here. By the way, when we do calculate, let me go back one. When we do this calculation here or here, we're going to probably get a decimal. What we're basically saying over here is to round up. Round up to the larger integer. Because if you round down, then you won't get within the margin of error that we had wanted. So here's our example here. Many companies are interested in knowing the percentage of adults who buy clothing online. How many adults must be surveyed in order to be 95% confident? So 95% is our confidence level. That means that alpha is equal to 0.05. That means alpha over 2 is 0.025. And that means that z sub alpha over 2 is equal to 1.96. You're going to see 1.96 crop up many, many times associated with a 95% confidence level. So how many adults must be surveyed with the 95% confidence that the sample percentage is in error by no more than 3 percentage points? So we're going to set E to be equal to 3% or 0.03. We're going to set that as our upper limit. Now, we do a little bit of research and saw that from a previous study by the Census Bureau, 66% of adults buy clothing online. Now, look, we're going to do our own survey, but we could use 66% or 0.66 as an estimate of p hat when we calculate our sample size. Otherwise, if we don't trust this, we could just assume that we have no prior information in calculating our sample size. Okay? Now, if we are going to go with the Census Bureau's statistics, then we could use p hat to be equal to 0.66, and then that means q hat is 1 minus that, which is 0.34. Z sub alpha over 2 is 1.96. Margin of error is 0.03. And put all that stuff together in a little formula right here. Here we got 1.96 squared times 0.66 times 0.34 divided by 0.03 squared. And you get 957.839. Round that up. Always round these up to 958. And that'll get us within 3 percentage points for margin of error. Okay? That's our sample size, our minimum sample size. Now, if we do not trust the 0.66 or 66% figure from the Census Bureau, then we could just assume that P hat and Q hat are both 50% or 0.5. So we could just plug in 1.96 for Z like we already had, and E is equal to 0.03. And of course that's going to give us a larger sample size, a 1067.1111, round that up to 1068. Again, always round up. Okay. Again, you're always going to have a larger sample size if you don't already have a good estimate of P hat or Q hat. That's much different than 1/2. Okay. Now, if it happens that you already know what a confidence interval is, but you don't know what P hat or E are, then you can calculate P hat as the average of the upper and lower limits. Because after all, on the real number line, this is P hat, and on the lower limit you have P hat minus E, and on the upper limit you have P hat plus E, where P hat is exactly in the middle. So it's like the midpoint of this interval. So this is how you calculate the midpoint. You just take the average of the upper and lower limits. It means that you add the lower and upper limits together and divide by 2. Margin of error, well, look, the width of this interval here is going to be 2 times E, huh? So to figure out what E is, you just find the width of this interval by taking the upper limit minus the lower limit and divide by 2. All right, you'll have a chance to practice that on the homework, okay? So with that, we are done for today. I'm going to go home. And you folks have a good weekend, okay?